Our goal in studying infinite series is really to get to these things called power series. So, what are power series? Well, really, it's just an infinite series that's a function, right? So, we're looking at series of the form sum from k equals 0 to infinity of ck x minus a to the k, right? So, we're looking at series like this. Generally speaking, this series here, it will at least converge for x equals a because everything is going to be 0. But we're interested in saying, well, on how big of an interval could this converge? Right? So here, each ck and a, these are real numbers. Okay? The terms here, these are called the coefficients. Oops. Coefficients of the series. Right? This thing is called the center of the series. All right. So the way a power series sort of works is it will always converge at x equals a, and then we want to know sort of how far away we can go from that. So we say that the interval of the form minus r to r is so the interval on which the series converges this is called the interval of convergence. Oh, sorry, I messed up a little bit. This isn't just minus r to r, but it's minus r plus a to r plus a. Right? So again, this interval is centered at a, and it moves a certain distance to the left and to the right of a. Right? So this interval is called the interval of convergence. All right. Convergence. All right. And r is what's called the radius of convergence. All right. So again, what we're sort of doing here is saying, all right, starting at x equals a, kind of what sort of one-dimensional circle can we make on which this series converges, right? So we'll talk about how to compute the radius of convergence a bit later, but a little hint is it's going to involve the ratio test, right? So this is just a little overview of what we're getting into. Let's go ahead and sort of see an example of representing a function as a power series. How can we get this? Right? So what's one way we can represent a function as a power series? Well, let's consider f of x equals 1 over 1 minus x. Right? That's a perfectly nice function here. Okay? So how can we get a power series for this? Well, one trick we can use is to recognize that this kind of looks like the output of a geometric series. So 1 over 1 minus x, this will be, if we think of this as a geometric series, which remember has the form a over 1 minus r, this should equal, actually this is f of x. Right? So here, a geometric series starts at 0, goes to infinity. A here is 1. R here is x, so this is sum x to the n. Oh, sorry, x to the k. Right? But now the question here is, where does this actually converge at? Well, geometric series also, remember that converges if r is less than 1, our absolute value of r. So here we would say for absolute value of x less than 1, which as an interval, we would write this as -1 to 1. Right? So here we could say that the center equals 0, and the radius of convergence, right, since the center here is 0, and this is 0 plus 1 and 0 minus 1, the radius of convergence is -1. Now again, we'll talk about a better way to compute the radius of convergence afterward, but this equality is true only on this interval here, right? That's an important thing to point out here. So while this function is defined everywhere except x equals 1, this series is only equal to this function for x less or between -1 and 1, right? So this is just one way we can get our hands on some examples of power series. So let me talk about another thing we can do with power series, which is we can integrate them and differentiate them. By doing this, we can create a whole bunch more power series. Right? So I'm going to call this a theorem here. All right. So let's say that we have the series ck x minus a to the k. And let's say this converges on, I'm going to write in the 0 to infinity stuff here. Let's say this converges on x minus a less than r. All right, so here, this is another way to write that interval, r minus a to r plus a. Okay? Or sorry, a minus r to a plus r. I said that backwards. All right. Okay, so let's say we have this here. Then, all right, actually, I want to say and defines a function f on this interval. All right. So what we're saying is, this series converges on this interval here, and so we're going to call this series f of x. Right? So what we can say then is that f is differentiable on this interval. Right? And why should that be true? Well, we're essentially saying that this function is equal to this power series, but look at what that power series is. That power series is just a glorified polynomial. That's the really impressive part of writing a function down as a power series, is that we're essentially representing a function by an infinitely large or infinitely long polynomial. Sometimes finite, but usually infinite. Right? So it's differentiable here, and to find the derivative of f, we just differentiate each term. Right? So actually, it's a good idea to maybe leave these off. All right? So we just differentiate this term right here. You know what? It's fine. We'll leave it there. You really want to be careful here, because this will now start at 1. Because when k is 0, this sort of isn't defined anymore. But yeah. All right. And again, this is going to be on the same interval. This will be defined. Right. Now, not only can we differentiate a series, we can also integrate a series. Right? So we could say the integral of f is, well, integral of f of x dx. As you might expect, we just integrate each term of the series. Now here, because the constant term isn't going to go away, we can keep this starting at 0. And what are we going to get? Well, it's just going to be ck x minus a to the k plus 1 over k plus 1. So just like with differentiation, where we can do it term by term, when we integrate, we can also do that just term by term. But here, we have to add a big, arbitrary constant on the outside. That's excessively big, but... and again, this will be defined on this interval around a. Okay? And the c here is our usual arbitrary constant. Right, like we would usually have when we do an indefinite integral. So, let's look at this then. What are some things we could get out of this? Like, how is this helpful to us? Right? Well, let's look at some other examples. Right, so since we can differentiate and integrate term by term, right, so let's recall that if f of x is 1 over 1 minus x, then, we can represent this as this series, right? Well, what if I wanted a series for, what if I wanted a series for the derivative? Right? The derivative of this thing is 1 over 1 minus x quantity squared. Well, to get a derivative for that, I just differentiate this series here. Right? I just differentiate this. And to differentiate that, I can just differentiate term by term. Now, something that's a good idea here, I think you'll find, as you do more of these, is that it's a good idea to sort of write out some terms of this series. Right? Just so you don't have to worry about messing around with the indices here. So here I'm going to write out 1 plus x squared plus x cubed plus x to the 4th, and so on. And now I'm going to differentiate everything. So the 1 will go away, and I'm going to get 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot. And the reason I think it's a good idea to do this is, it'll be you'll get a nicer looking series at the end. So here, this pattern here will give us k equals 0 to infinity. The powers are x to the k each time. And the coefficient is actually k plus 1. Right? So if we just differentiate it directly from here, we're going to get the sum. Now here, k will come down. We get x to the k minus 1. And here, that first term is going to be 0. So really, this would start at 1 to infinity. But if we do some reindexing, we can change this to this here. Okay? All right. So this right here, this is a power series for the function 1 over 1 minus x quantity squared. Right? That's pretty neat. Now, what's actually even more neat is looking at this one in the other direction. So if we look at the antiderivative f of x dx, right? So the antiderivative of 1 over 1 minus x dx, this is negative ln absolute value of 1 minus x plus c. Okay? And actually here, since this is only defined for absolute value of x less than 1, all right, this here we can drop the absolute value on because this is never going to hit 0. So we could just say negative ln of 1 minus x. All right, just to make life a little bit easier. All right, so that means we can just integrate that original power series, right? So let's integrate the power series part of it. All right, so I'm gonna say, all right, this is the integral of, let's write out the terms of that series just like we did for the derivative. So the integral of 1 plus x squared plus x cubed, and so on, dx. Okay. And so what we get is x plus 1/2 x squared plus 1/3 x cubed plus 1/4 x to the 4th, and so on, right? Oh, plus, now here I want to give this a different arbitrary constant. So maybe let's call this one C1 up here, and this one C2. Okay? So what that means is, these two have to be equal to each other. Now, what we can do here, right, is we want to figure out, well, maybe what about a power series for just ln of 1 minus x? All right, what if I just want that part? All right. So this function has to equal this for some choice of C2, right? Because these two just differ by some constant. So what do? We just plug in 0, right? So ln of 1 minus 0 is ln of 1, which is 0. And let's plug it in here. Oh, sorry, I need the negative of this. Okay. All right. Because when we integrate this, we get the negative sign. Right? Now let's plug it into this series here. So that would be, we're plugging in x equals 0. So plug in 0, 1/2 of 0 squared plus 1/3, 0 cubed plus 1/4, 0 to the 4th plus C2. Right? And all that's going to be left over is C2. So by equating these two, we know C2 has to be 0. And so negative ln of 1 minus x is equal to x plus 1/2 x squared plus 1/3 x cubed plus ... Right? And so ln of 1 minus x, just get rid of this negative sign here, it's going to be minus x minus 1/2 x squared minus 1/3 x cubed minus ... And that is the series k equals 1 to infinity, right? Important to keep that in mind there. X to the k over k. Right? Oh, sorry, negative. Right? This is ln of 1 minus x. So we can use, the trick of a geometric series together with differentiation and integration of series in order to find power series expansions of functions. And again, I want to emphasize this is good for x less than 1. In fact, that should probably be in the box as well. Right? So as long as the absolute value of x is less than 1, this power series equals this function. All right?